Wonderful. So we'll go ahead and get started. Today we're going to be introducing SolidWorks simulation. My name is Enrique Garcia, and I'm one of the simulation specialists here at Go Engineer. Been doing this for a while. So see a bunch of familiar faces here. It's been wonderful to see you all. So today we're going to be talking about some foundational topics that we need to understand before we use simulation, and any simulation tools, to be honest. Whether that's Abacus or ANSYS, these are all foundational topics I want to cover. And then we're going to do an overview of the workflow that we use in SolidWorks simulation. Before we get started, here's a slide that I want to show. Let me pop that on here. A little bit about who I work for before we get started. So I work for Go Engineer. You all may know us. So for those of you that aren't familiar, we're a reseller of SolidWorks, and we have quite a bit of engineering tools and resources at your disposal. We offer products from 3D CAD modeling, simulation, scanning, 3D printing, as well as consulting, to name a few things. I myself specialize in knowing simulation, presenting simulation, as well. Yeah, I just really enjoy doing presentations and visits and things whenever I can. Let's go and continue on here. So, slide about myself. Like I mentioned, I specialize in simulation products. I've been doing this going on my 16th year, coming up next September. So it's been a minute. It goes by really quick. I had planned to go into industry right after college. I worked a little bit with a company called Kinetic Muscles, startup in Tempe. They specialize in orthotic medical devices, class 1 devices for therapy purposes. I learned how to be dangerous with simulation with that tool at that time. And I decided to go into, I was going to go into industry. We had a kind of a crisis back in the day, and the housing crisis about 2008, 2009. And so I had to stay local, and I ended up finding a reseller that sold SolidWorks, and I didn't know what an application engineer was. And I thought it was a great way to kind of stick around and get some certifications and move on. But I kept learning something new, and I really enjoy learning new things and tinkering, talking to people about things, and connecting everyone. The collaboration aspect has been fantastic. So that's why I'm here, just to be able to collaborate and talk with all you fine folks and show you things that I've accrued over the years of my profession. Speaking of being a tinker, I've been making toys and 3D printing. Once that came out, I caught the bug hard on 3D printing and tinkering things, Raspberry Pi stuff, and that's been fun playing with all that. So made a lot of toys during the pandemic. I was kept my sanity that way. Before I begin, I just wanted to show, here's a fun simulation project that I did for my nephew, Jack. He's a huge Spider-Man fan, and so he wanted some specific Spider-Man web shooters so he could fight some crime in the neighborhood. So I made these things up and modeled them up. I used the master model technique in SolidWorks, and I just realized these 5, right? So I made the triggers too thin. He was going to blow and just break these things in 30 seconds. So I just did a quick test to see where the stress hotspots were. And, we have tribal knowledge of these things as well, but it's just always nice. And it's easy just to go into the simulation tool and do up something and kind of correlate with what you're thinking, right? So it helps, not for my application specifically, but in many applications out in industry, you just want to do a quick spot check just to show that the math works out to what your experiences are telling you is going on. And so yeah, I did some structural analysis on the triggers, adjusted the design, made them a heck of a lot thicker. And I think he's on his 3rd replacement set. He's 5, right? So just some fun there. Here's an actual simulation project I worked on a few years ago. This was regarding a court case here in the Valley where there was a detected propane leak. And so there was this room or a trailer maybe, and basically the doors opened and closed during a certain time, and I guess there was an explosion. There was a fatality as far as I know, and this is all that the customer would give me on the white sheet. They're like, hey, could you prove that the the concentration of propane was enough in this volume of air for there to trigger a spark and explosion. Is that possible? And I said, well, I can try. I can go in, I grab the parameters of the room, set up a flow simulation study. And this is what the analysis was. I did a tracer study, and this is what showed as far as the concentration. As you can see in the blue area, there wasn't much of a concentration of propane. So came back and concluded that there was not enough concentration to trigger the explosion based off of the simulation here. So it was great to hear that the expert witness also came to the same conclusion. So just a little bit of background of where I came from, and let's talk about the agenda for this presentation. So we're going to start by introducing simulation. What is simulation in general? This is just a 3,500 foot view of what the simulation tool is. Then we're going to talk about some of the foundational concepts to simulation. Then we're going to go in and do some workflows. I want to walk through setting up a part file, just something simple, maybe something on the funner side to kind of go through the workflow here with you. We'll do some interrogation of the analysis of the part. And then we're going to talk about interactions. So even though this is an introductory presentation or seminar of simulation, contacts and interactions are very important, not just for our simulation tool, but for any tool. Understanding how these rules work is going to make or break and give you meaningful results for a simulation. So I like to talk about them, give you, again, an introductory lesson of interactions. And then we're going to review a setup of an assembly towards the end. So that's the workflow, that's the game plan. Any questions before we get started? Let's do it. All right, so we are talking about FEA analysis here. So it's just a numerical method. If you guys remember college, you took numerical methods in school. It was just, it was repetitive, right? It put you to sleep sometimes, but it was necessary. And this is why. This is the back end of what happens when you're running simulation, is the numerical method. For us, there's a process of setting things up called pre-processing stage. And we'll talk a little bit about that more, but ultimately we're just putting in this numerical method into use. It's packaged in SolidWorks, and I think that is the meal ticket here. Anyone can buy, there's many options for simulation FEA analysis, but this one is just built into the SolidWorks ecosystem. So again, it's the convenience factor. It's going in and setting up the analysis, getting results, going back to the CAD model, all within the software, making a change, going back to the simulation and updating it, just hitting run and letting it mesh and update and run, getting different results. So just because it's easy to use, it's also a high-end, sophisticated software. You can't change math, right? So it's the same foundational capabilities that we have with Abacus or ANSYS. There are some things that are simplified to make it easier, but it doesn't mean the results are going to be any less meaningless. We can do pretty sophisticated things like optimization. We have composite materials we can work with, dynamics, nonlinear dynamics as well, fatigue solvers, to name a few capabilities that are sophisticated up there. So here's an overview of all the simulation tools that are built into the SolidWorks software. So we have SolidWorks Simulation, which is our FEA package. We have Flow Simulation, which is on the left-hand side there. That works and that deals with our fluid dynamics capabilities. We have that ability as well. And then we have SolidWorks Plastics, which deal with thermal injection plastics. So all these simulation capabilities can be used natively inside of SolidWorks. For us today, we're going to be focusing on the static structural analysis for our examples. So again, the reason I show this is because this will give you a good foundation for most workflows that you do within the SolidWorks ecosystem. All right. So there's a process when you're doing simulation, any simulation software. We have traditionally 3 phases or stages in working with SolidWorks simulation. So this is traditionally, we have the pre-processing stage, which involves working with the CAD model, setting that up, getting it ready for simulation. That can involve simplifying the model, removing features, idealizing geometry, all that stuff. It also involves setting up and picking the actual study that you're going to use, whether it's a static study, a thermal study, or a nonlinear application. So setting that all up is part of that pre-processing stage. Then we have the solution. That's an easy one for us. This is just hitting the run button. We have solvers that are already chosen and curated with simulation. We don't have to worry about purchasing things separately. and then we have the post-processing, or the post-processor. The post-processor is, I think, one of the main attractors to the tool as well. It's easy to use. It gives you qualitative and quantitative results intuitively. If you're used to using SolidWorks, as we are, it's going to be a lot easier to use these tools. Now, the reason they're broken down in these three categories is because traditionally, this is how you buy simulation software in industry with Abacus or ANSYS. You go in and you purchase a preprocessor or a GUI basically first, right? And then so you can go in and load your model on that and set things up on that. You usually have some rudimentary CAD capabilities with it. Nothing fancy, but we have stuff to make holes, and it's become, over the years, you get more features along the way, but we have a rudimentary CAD software in that GUI, and then we can set up the study in that. And then separately, you had to go in and buy the solver separately. If you're doing a thermal analysis, well, you go and you shop around for the thermal solver that you're going to be running the data through. And usually people will forget to buy the post-processor. So I've had a lot of students and acquaintances over the years tell me that they had a project and this was their first big thing for their company. They bought the pre-processor, they bought the solvers, but they forgot the post-processor. So they had this output file and they didn't know what to do with it. They needed qualitative plots, right? And so they just bought a post-processor, and it was a horrible experience. And they basically had shelfware. So SolidWorks will package all this together. So if you need to run simulation, you just get the simulation software. It has everything that you need. It's curated. Think of it as a curated set of tools. What else? So again, the SolidWorks UI brings them all together. I mentioned with the preprocessor that you want to simplify and condition your CAD model and get that ready for simulation. And I like to mention this, and I want to talk about this a little bit, because this is something a lot of my students, when I teach class, and myself as well, fell into when I did my first project, my first real project. I basically got the model from my client, and it was an arm curler, I remember, from Lifetime Fitness, and they wanted to know some hot spots and things. Nothing too crazy, but it was a production-ready model, right? So I got the model, I set it all up, and I wanted to mesh it. It failed. It gave me a heck of a time to get it to mesh. And I asked for help, and they're like, "Oh, you're an application engineer. You should know how to do this, Enrique." So I had to figure it out. And what I was missing is I had too much detail in the model, and that's huge. Getting and simplifying and conditioning your CAD models for simulation is a essential part of this whole workflow I'm talking about. So there's a couple of things you want to do when you're going to run the model. And they're up here on the slide. Is defeaturing is the main thing. Whether that's going in and maybe making a copy of the assembly or the model in general. I recommend doing a file pack and go. Who here uses pack and go? Yes, perfect. So do a file pack and go. Use a prefix or a suffix to have unique file names. So it's completely detached and denatured from the original file system of files. And then for that one, then go nuts. Go in and defeature, suppress things, or even delete if you needed to, but simplify the model in that way. Something else you could do is maybe if you can't detach yourself, if you have a file management system where you cannot do that, if everything's tracked, you can also maybe make a configuration and call it simplified or call it FEA configuration, something like that. And then in that configuration, then start to carefully suppress features that are detail-oriented, things that you think as an engineer are not going to be it's not going to elicit a response from the model. Things that are detail oriented, diamond plate features or small holes, small fillets, things of that nature. Defeaturing is a huge part of this pre-processing of your CAD data. The other thing you want to consider is going to be the idealization of your models. So idealization is the replacement of your CAD design or aspects of your geometry with simplified versions. For example, like this laptop or maybe this projector on this small table. Well, you can, if you don't need to worry about what's going on in the response of the projector, but maybe the table, then replace that whole projector with a simplified rectangular extrusion of the same mass, the center of gravity, and then use that instead. So you're replacing it with simplified versions of geometry to make this simulation study simpler and easier. And that's the goal. And this brings up a good concept that I want to just spearhead all this with and make it your cornerstone when you're doing your simulations is start simple with everything. Start simple with your CAD model that you're using. Start simple with your setup of your simulation. Don't go nuts with setting up everything exactly how you want it to begin with. Start simple. Start with a standard material, maybe simplified fixturing and constraints and forces, and also a coarser and simpler mesh. Those three things, make them simple, and then slowly start adding more detail to all three. And that's how you want to give yourself that insurance in the end. You'll get a ballpark figure in the beginning, right? But it's going to be easier to troubleshoot when things fail and go wrong, which they will, right? We've all been there. We all just want to throw our machines on the street, right? Sometimes. So start simple so it's easier to troubleshoot errors, then slowly start to put your foot on that accelerator and add more detail to the geometry, more detail to the setup, and more detail to the mesh. So you're converging all three aspects of your simulation. So again, that's a lot, but I like to front load that concept. That's one of the biggest concepts in all simulation. All right, one more thing here is model cleanup. Who here imports from another modeling kernel into SolidWorks? Anyone imports geometry? A few of you? Okay. So yeah, this is going to be important for some of you all, is cleaning up your CAD data. Sometimes just double check to make sure that if you have importing a solid geometry, that it's imported successfully as a solid, not a surface body. Double check things. We have in SolidWorks the import diagnostics utility that does a decent job at automatically fixing things. It's the closest thing to a do my job button we have in SolidWorks, right? So we have that capability that you can play with. Also becoming somewhat of a surfacing guru is I think a good tip in general, even though we're simulation people here or interested in simulation, being able to use the surfacing tools to resurface or delete face and patch. All of these features are going to be really helpful to fix imported geometry. So model cleanup is going to be huge when you're doing simulation, potentially if you're importing. Also, when you're importing, it's a good idea to import with Parasolid as a dummy body. If you're going to be doing that, that's the modeling kernel we use in SolidWorks. So import as a Parasolid whenever possible. Any questions on this? All right. So last topic I want to talk about here is assumptions. So with simulation and with anything, right? If you have, I call this the garbage in, garbage out principle. If you have poor assumptions going in, well, this is a tool, you're passing it through a tool, you're going to have poor quality results coming out. So to have meaningful results, we need to make sure that we have certain things that we can agree upon. In this case, we're going to be doing a static study. So these are the assumptions we have to make when you're dealing with a static simulation study and simulation with SolidWorks. The first assumption here is that the materials involved will behave linearly. So linear responses will be dictated basically by the elastic modulus here from the picture in the slide there. So again, that's where we live when we're dealing with the response of the model inside of a static simulation study. If you needed to do something more nonlinear, we have you covered with a nonlinear study. We can enter a stress strain curve and get that response pretty easily with the tool. But that's the biggest one, right? Is making sure that we understand what that means when we're dealing with the software. Now, what comes hand in hand with the linear portion of that stress strain curve as a response is that small strain, that relatively small strain, right? And what is that? That's a derivative of displacement. So because of that, we have our second assumption that the deformations of the geometry are small. So because of that, we have to abide by that rule. Now, that can be subjective, right? So what is a small displacement? So luckily for us, the software, when we hit that run button on a static study, it will give us a message. You guys have probably seen it if you've used the tool. It says something about excessive displacements were found, yada, yada. It gives you then a bunch of verbiage, right? We just say, no, get rid of that, click cancel, right? So what that's telling you is that, yeah, you're now probably flirting with the boundary between a linear response and maybe a nonlinear response of a model, because it sees that it's projecting a larger displacement. So I'll talk a little bit about that and what that means and how to maybe deal with that situation a little later. But just know that's our second assumption. The third assumption is pretty self-explanatory, is that all of the applied loads are static. So we cannot change a force as a function of time in this case. So there is no time variable. So if we needed this behavior, we have you covered with a dynamic study. We can do that. You can, maybe to kind of push the limits of the tool, you can run a dynamic study if you can assume that the inertial forces are negligible. You can do that. I had a customer it was a prospect. They wanted to buy dynamics or simulation premium because they had a dynamic application. Well, it turns out their dynamic application was simpler, and the inertial forces were not even there. So they were able to hold off on that and maybe save a couple of help them save from having to buy the more expensive tool for now until they really did need it. And they were able to do their application with the static study. So just know that as long as you can apply a force slowly, where inertial forces are negligible, you can admit that. Reminds me about my thermodynamics teacher at the Arizona State. He said, your job as engineer is to say negligible many, many times. He was this awesome Greek professor that we had. He was great, good mentor. But yeah, those are the assumptions you make with our simulation tool. Any questions before we talk about a case study here? All right. So now that we have a good foundation of some of the topics that we need to do a simulation study, we're going to do a study on the Sony Aibo. Who here has heard about the Sony Aibo? Anybody? Oh man, let me tell you about this. This is a product from the future. So picture this. So I was 12, how old? Yeah, about 12 maybe, or 10 years old. On television, this robot dog shows up, the Sony Aibo. I lost my mind. I thought the future is here. This thing had voice recognition. It had infrared vision. It had a bunch of sensors on its paws. You could pet it. It could do tricks for you. It was a dog, right? That responded to you. So it responded more than my own dog at the time. And so I asked my parents, can I have this dog for Christmas? It's so awesome. It's a Sony Aibo. It does this, it does that, color recognition, blah, blah, blah. My parents are like, yeah, I can get you something like that. You know, just arm waving that away. Turns out that this was, as we get older, right, the toys don't become toys, they become collectibles, right? So this was more of a collectible. It was about $2,000 back in, gee whiz, 2000, I think is when it came out. No way I was going to get this, right, as a toy. So they said, oh, Santa must have messed up. And so I got something else, right? So, but core memory, right? This was something that I remembered. Fast forward to a few years ago, I found someone in Japan that we refurbished antique robot Aibo, Sony Aibos. Started chatting with the guy. I felt good about it. I pulled the trigger on one for a couple $100, which was a good deal, considering, you know, this was a cornerstone memory for me. Fast forward to the point where it broke. I broke my robot dog. So it had like a sit condition, and it failed, and it started walking, cracked its neck. You can see on the lower left-hand corner there of the screen, I have a piece. It was what I call the yaw plate, which pivots the head and moves it back and forth, left to right. That just snapped. The actual neck part, it snapped. I was able to epoxy that. That was fine. But this part, it was hard to find. I tried maybe putting it back together, but I thought, hey, what a good opportunity would be to crack this thing open. I'm a tinkerer. Well, to kind of play around with this thing, maybe I can see how it ticks, and maybe I can fix the part with using my tools that I work with every day. So sure enough, I went in and I took some pictures of the model of that part. I used sketch pictures to import it into SolidWorks on that lower right-hand corner of the screen. Simple part. Got it redesigned, basically reverse engineered it. And I thought, well, let me install it. But before I install it, I'll 3D print it. And it came out okay. It was kind of newer to 3D printing. But then I thought, hey, but let me see if I can optimize this thing, right? I have simulation. First of all, let me see if I can correlate this to what actually happened to real world results. What a good experiment I can show for kids. And when I go and show this to people and things. So that's what I ended up doing. I went ahead and we're going to try to run through a little example of how I set this thing up. Whereas ideally, yes, this is going to be a dynamics application, right? It's an impact that happens. So I'm making some assumptions and I'm starting simple. That's the workflow, right? You start simple with your study types as well. And then, yeah, as in the second phase, if I needed to get more detail of this analysis, the next phase would be to do a dynamic analysis and impact testing, shock response or something to check it out. So this is what I'm going to be doing. I'm going to run through a little example where I'm setting this guy up with some fixtures. I am assuming a static scenario where this maybe is instantaneously impacting. I'm getting a force, which the force is coming maybe from the servo, and maybe where those three little holes there, that's what it gets attached to the actual head of the robot dog. So that's going to be my point of where I'm going to be fixing the model. On the top, I need to make sure that this cylindrical section is going to be plugged into the housing so I can rotate that, but I can't translate up and down. The thing is made out of a generic ABS plastic. So we'll pick that to start as my material. Then for a load, I'm going to do a little torque load on this thing. Again, I'm taking maybe I think the robot dog weighed about 4 pounds. And again, this is going to be for maybe ideally an impact dynamic analysis. So I bumped it up a couple of units to 6 to see. I want to see where the stress hotspots are to start. And that's the goal for this static study. And then I'll set this thing up with a mesh. And for those of you that are new to simulation, the software, think of it as the mesh as a way to sample what the geometry is. If I set everything up in simulation and then hit run without meshing it, the software can't see the actual model. The mesh is how it feels what the geometry is. So the more mesh elements and more calculation nodes in it, the more detail it can feel for when it runs a study. So it knows exactly what the geometry looks like. So I explain it that way because the more detail you add, yeah, the more you can feel, right? But if you add more resolution to it, you can't really feel any more detail at a certain point. And that's a similar idea with a solver. You can add more calculation nodes on this thing, but more calculation nodes doesn't necessarily mean more accurate up to a certain point. So you have to find that sweet spot when you're playing with these tools. So let's go through a little example here. I'm going to open up SolidWorks simulation. Let me close this out for now. And let's jump over to simulation. And let me switch over to the screen. See if I can get that to show. Let me re-show, for those of you on the Zoom meeting, let me re-show that one more time. Bear with me if you're here local with me. Let me try to get this. Yeah, I did that. So, duplicate. Thank you. No, I think I did. I think I fat fingered it. There we go. Thank you much. All right. And let me just check on chat. Can everyone see my screen okay? Can someone give me some quick feedback?
Yeah, we can see it. There's
Perfect,
a weird block in the middle on ours. I don't know if that's on purpose.
On the top, it is. It's the meeting software. For some reason, it's not sliding back in like it usually does.
It's also set. Oh, never mind. Yep, just on the top.
Just on that top, right?
Yeah, just on the top.
Let's see. Yeah, right. I think for now, then, just to I would be able to show that. Let me do this. Let me just bring that down. Do some. There we go. That'll work. The easiest solution is always the most
Perfect,
efficient, I
thanks.
guess. All right. All right, let's keep on going. So I have this example here. This is the Sony IBO yaw plate and that I reverse engineered. And I'm going to start a quick simulation study here. Now, when you have simulation, you can turn it on just by going into the add-ins in SolidWorks. So I have the SolidWorks simulation add-in here turned on. That gives me two things. It gives me the simulation tab in the command manager, and it gives me a dedicated menu pull down in the general UI. Depends on your preferences. Both ways can be used to start new static studies, and it gives you access to different tools for simulation. Basically, just like any SolidWorks tool, right? There's many ways to skin a cat with these softwares. So however you feel more comfortable using the UI. So I'm going to click New Study. We have all these different simulation types depending on the licensing you have of simulation. So I'm going to pick static here for me. You can give it a custom name if you wish. I'll just leave it whatever the default is. And now you have a new simulation study. Now, if you needed to go in and set up a simulation study, this is where you need to be. However, when you go back to the CAD model to make a change, it's really easy to go back. You can click on the model tab on this lower left-hand corner of SolidWorks, get to all your different features, do what you need to do. Then if you needed to go back to your simulation study, click on the tab. Basically, all your simulation studies are managed on this lower left-hand corner, just like Excel. Think of Excel, how you go in and you right-click and you manage different things. Well, you can go in and rename tabs or study names. You can delete things. And my favorite is copy study. If you set up a static study that maybe is perfect, but you wanted to do some investigation with a different material or maybe a different constraint, copy the study, right? So you have less human error, and then make the one change and then go ahead and rerun that. All right, so setting up a simulation study, it's working. You basically set this up as you would with different folders, just like you would with SolidWorks in general. Whenever you add a piece of work or a feature, it'll show up nested under its corresponding folder. So the way I approach a setup with simulation is I like to start from top and just work my way down from top to bottom. So I'm going to start off here with the material. If your CAD model had already assigned a material, it'll go in and bring that in, whatever that material definition was during the initial creation of the sim study. In this case, I didn't, so I'm going to pop in just a generic material. You'll see here that the materials database is the same for simulation as it is for SolidWorks. So that really helps out. I'm going to go in and just pick that ABS plastic that comes with simulation. Notice that it doesn't have a yield strength, right? And that's by design. There's many different batches and types of manufacturers of ABS plastic out there. So just quick Googling on MatWeb, I think the generic yield strength for this ABS plastic was like anywhere from 13 to 65 megapascals. So we just take that, think of that, maybe keep that in mind when you're looking at results. So I'll go ahead and apply that material. And again, I like to go from top to bottom on my folders to work through this all. So I look at my connections next. Do I need to add any feature in here for this one single solid body? Yeah, I don't. This folder is only for when you're interacting with multiple components or multiple bodies in a simulation study. In this case, we're focusing on the response of just the one part. So we're going to move on from that. The next thing we're going to do is apply some fixtures. And yes, we're going to be fixing the model with this more popular fixture called fixed geometry. And I'll go in and I'll pick maybe these cylindrical surfaces and then the slotted surfaces. That's, again, going to be interfacing with the geometry of the robot's head. So, and then we click OK to apply this. Again, just like a feature, right? Like when you apply an extrude feature in SolidWorks, you click the green check mark, it gives you a symbol in this case. And if I needed to go back into that feature to fix it or change it, it works just the same way. I can right click, I can manage it with suppress and hide, or I can edit the definition of that feature, change it completely, or add new faces or reference geometry to the thing. click to close or click to edit. So that's one of the constraints I want to add. Now I want to focus on degrees of freedom of the model. I want to make sure that it doesn't go up and down, but so I want to make sure that maybe I limit that particular face. There's many ways to limit degrees of freedom, right? So the way I'm showing you isn't the only way you can constrain the model. It's a way you can constrain the model. So I'll go in and maybe go to, we have quite a bit of different ways to do it, many ways to apply constraints. You can see the GIF file here, and we can kind of go through what those show, what those mean. For me, I'm probably going to stick with maybe, let's do, oh geez, maybe that guy, and we'll do standard. I'll do like a roller slider for that one. This way we're limiting the translation up and down, but we're letting it move and rotate along the XZ direction for now. So I'll click and apply that guy. Now to limit this, but it still allow it to hypothetically rotate or respond in rotation there, as if it were maybe plugged into a housing or something. So I can maybe use a cylindrical reference for that. Maybe right click on fixtures, go to advanced fixtures, and we have a cylindrical faces option. I can click on that. Yeah, that's the face I want. That one on cylindrical faces. Now down below, we have the degrees of freedom that we can constrain. For me, I basically want to constrain the radial degree of freedom. I don't want that face to radiate outward as a response to whatever I'm doing for my force load. So I'll leave it at 0. I'm leaving this open so I can hypothetically respond and turn there. And then I'm leaving the axial so I can let it go up and down, which I've already constrained with the top. Right? So there's many ways to be able to constrain these things. This is not the definitive way of constraining the model. So that's one way. Next, let's talk about loading the model, right? So we know that we have to have a force load. In this case, we're putting a torque on the interfaces of the geometry that interfaces with the servo motor. So for me, I'm going to right click on the external loads folder there, and I'm going to go into, let's go to torque. And I'm going to be picking, let's just pick these larger faces for convenience. You definitely want to do the smaller ones. And again, this is a simplified setup. So again, I may want to go back later and maybe readdress that, make it a little more simple, a little more realistic. So I'm choosing that, and maybe I want to go around the wider the rotation around the Y. So I need to pick a reference. So I'm going to be picking either an edge, a cylindrical face, or a circular edge. In this case, a cylindrical face. We can see now the arrows are pointing in the appropriate direction around the geometry. Down below, we can enter a magnitude for this torque. So SolidWorks simulation works with what are called true units, just like SolidWorks does. So if I enter a value and I change the unit, it's going to convert the value. So you have to be careful with that. So just be aware of that. For us, we're going to be working in IPS, and we want this to be units. We said 6 pounds force inch, so we'll pop in 6 on that. And down below, we want this to be a total of this value, not per face. So gotta be a little careful there. The devil is in the details, right? Always question your results. If you're looking at your results and they seem wrong, if they're ballpark, yeah, you might be barking up the right tree. But if they just seem way off, right? Go back and look at small details like that. I guarantee 90% of the time it's something you did, something we've done to maybe change a direction vector somewhere or something like that, where it's maybe per item instead for the total geometry for a reference for something. There's always something, right? There's a decimal error, something like that will happen. So we'll click total on that, click OK. And also we can hit reverse direction too. Doesn't matter for us, but we can change the direction of our rotation of our torque there, of our torque load, and click OK. All right. The last thing to do is we need to discretize our model or have the solver figure out what the geometry is. And we do this by meshing the model. Now that's the next folder here in our list in our design tree for simulation. We're going to right click and say create mesh. So there's a whole lot I can say about the mesh. for us, don't worry about it too much. If you're starting off, this is just part of it, right? Just you can really geek out and deep dive into theory of meshing and capabilities and things. So, but the nice thing is that if you're new to simulation, it's pretty forgivable. We use tetrahedral elements, which are really easy to mesh geometry in general. There's many different types of element types out in our engineering simulation, but we stick with a pretty forgivable and easy to work with element type for simulation in SolidWorks. So I'm going to go in. We have different things we can apply to this. I can maybe qualitatively move the slider to make the nodes between the calculations be smaller or larger. I have this is where I can start to geek out and dive into theory of meshing. There's different ways we can approach the mesh, but for now, I just want you to be aware of that we have a high quality and a draft quality mesh. For us, that means draft quality, we have less elements and less calculation nodes to deal with. If we have less calculation nodes to start, that is good, right? Because we want a quick start, we want a quick result set, something quick and dirty so we can see that we have ballpark results. Then we can go and maybe graduate this up to a high quality element, which have more element calculation nodes. And then you can start to play around with the mesh settings a little more. But that's a good best practice. Always start with a draft quality mesh for your very first or initial simulation that you run. So I'll mesh this thing up. Let's let me bump up the quality there a little bit more of the mesher. Let's see, yeah, I'll be able to bump it a little bit more. And that's what you're going to be doing as you're converging results, right? You want to converge what did we say? The geometry, add more detail, the setup, which is the materials, the way you apply fixtures and constraints. And then thirdly, your mesh. You want to start to add more detail in the mesh like I just did right now. All right, I think I feel good about this. The last tip here before we run this is to save and save often, right? I know I'm preaching to the choir on that one, so save it. Stuff will happen. Crashes happen, power failures, all kinds of things. Your dog, all kinds of stuff will happen. So let's go ahead and run this study. This one runs pretty quickly. How am I doing on time, Joe? Perfect. I just want to touch on two main things before we do another topic here to round off and close the seminar for simulation. We want to show qualitative results and quantitative results. So for qualitative results, we can add as many of these plots as possible as desired. SolidWorks simulation will add 3 as default of stress, displacements, and strains. You can add many other types of plots. So if you're new to simulation, just go play around with it. Add a plot, and when you add a plot, it'll tell you what it does. So in this case, a design insight plot. Yes, I'm going to continue for now, but then I can see what the message says. If the message is cryptic of what it, or it doesn't give you a message of what it does, click the help menu. That's one of the bigger tips I can give you, and read up on what it does. So the help menu in SolidWorks and simulation are world class. I've worked with other softwares and the documentation is extensive, but it's really hard to read. SolidWorks and simulation documentation are very, very good. I will say, comparatively speaking, you can really understand it pretty well. And there's examples and there's little GIF files and things. So I'm a champion of the help documentation and documentation in general with these tools. But that's qualitative analysis. Always go in and do an animation of your model. Make sure that they're behaving as you're expecting. And in this case, maybe with this, I want to maybe lower the, you can see what the maximum stress is there, right? So I said yield is anywhere from 13 to 65 megapascals, depending on many conditions, manufacturing, material manufacturers. But always I like to go in and show, this is just a pro tip, whenever I'm doing projects and I'm showing results, I like to go in and make sure that I edit the plots to show the yield strength of my material. Let's say I bump this to maybe 15. I override that just so I can more clearly see my hot spots. And yeah, that's exactly where the hot spots started, and it sliced and just catastrophically failed my part right there. So it was correlating pretty well to real world there. When it comes to your results, quantitative results, the primary way of using that is to use the probe functionality. Any of these plots, you can access qualitative results by using the probe tool. The probe tool can be used by clicking on any location in the software on the model, and it will pick the calculation node closest to your selection. It'll call it out here. It'll give you some statistical information. You can then plot that data as well. You can do that. Another thing you can do is trending. So I can say maybe at selected entities, and I can pick whole edges or faces, and I can collect all the nodes along, in this case, the edge, and I can look at data for that as well. So I can plot things. Any questions on setting up or questions on post-processing and simulation? All right. Oh, yes. Yeah. So on any active plot that you have, right-click on the plot, and then you'll have probe right in that right-click menu. Very welcome. All right. So the next thing I want to talk about before I show, I have maybe about 5 to 7 minutes left here, looks like, for my presentation. I want to talk about interactions a little bit. Who here has worked with simulation in the past? Perfect. Okay, yeah, that's a good amount. So a lot of you guys are also new, so this is really important. So let me switch on over. Let me recalibrate the meeting here back to how I was. And we'll do, you know what, just leave it here. It's just to make it easier. Just because we have it set up. Let's go back here. Oh, I guess one thing I can show. Oh, it did change that automatically. That's interesting. Oh, son of a gun. It took me all the way back here. Let me end that. Bear with me here, ladies and gentlemen. All right. There we go. We can see here, there's a correlation, and I want to show, start there, I guess. That's interesting. It kind of goes back to an extended state there. Really quick, want to poll everyone. Can everyone here online see my presentation screen?
It's showing the notes mostly.
Oh, interesting. Okay, let me switch it over. Ah, thank you very much. Let's switch that over here. Thank you. Now, everyone, now you guys can see that. Let me, son of a gun. Let me just do this here. Just duplicate. Let's just show it like that. All right, thank you so much. All right. So in the end, we get some correlation of results. There's a little picture of where the failure point was on the part, and that's the fix. So got that 3D printed, and yeah, it's still holding strong. So the next thing I want to talk about, and I don't want to take too much more of the time, but this is important, is interactions. So interactions is usually the bottleneck for your simulation studies. This is what takes a long time to understand and to walk through. There are some automated tools to add interactions in simulation, but as a user, a power user, a longtime user, I recommend there's no substitute for going in manually and vetting out all areas as much as possible, if not everything, every geometry area for your interactions. We're signing off on these results. And whenever, when I used to do tech support years ago, I would say 90% of the calls for simulation were, hey, my results are wrong. What could be going on? Is the bug? And it most likely was interactions. So they're particular. There's a way of thinking of interactions. And I want to give you that foundation right now. Interactions are located under the connections folder. And these are your 3 types of interactions. We have a bonded interaction, a free interaction, and a contact interaction. So bonded interactions are exactly how they sound. They're basically welding or fusing two entities together, whether that's an edge to a face, point to point, etc. Those are like you would think. The free interactions, those eluded me for a while. So entities can penetrate each other during simulation. You're basically ignoring purposefully pieces of geometry. Now, why would you want to do that, right? I had that same question for months, actually. Why the heck do we have a free interaction or contact set back in the day? And so it turns out this free interaction is for troubleshooting. Whenever you're respecting many geometries at once, that can be potentially a complex interaction event. And if you have too many interactions, the solver may be overwhelmed and there may not be enough calculation resources to pull to be able to solve and converge everything. It'll fail, it'll give you errors. So you can convert a couple of those contact interactions, the ones that respect each other, to a free interaction and keep a couple of them contact and simplify the interaction space for it to converge and run and solve. Then slowly maybe start bringing back some of those free arm waved away kind of interactions back to make them more accurate. So that's why it's there. Think of it as a troubleshooting interaction type. And lastly, we have the contact interaction, which that's a way that you respect your different geometries. There's ways that we can implement a contact interaction, but just know that this is the tool that we use to tell the software to respect and derive reaction forces off of and start to respond to each other's geometries respectively. Any questions on this slide? All right. So there are three ways that we apply interactions in simulation. There's a global interaction, which unless otherwise specified gets put on automatically. It's typically added as a bonded interaction. Whenever we open up our analysis here in a moment, you're going to notice we have a globally bonded interaction, which means any initially touching faces, edges, and points are going to be applied as bonded to start. Now, I recommend leaving it on as think of it as a safety net. Don't just toggle it off or change it. Leave it on, especially if it's a larger assembly. If it's small, like we'll see here, maybe we'll switch it, but leave it on to start, and then go in and locally apply interactions so that if I forget maybe a certain area, then maybe it'll be bonded in that area, and that's going to give you a little more of a conservative result anyway, a little higher stress, and that's typically okay. So that's global interaction. Then if the other interaction type is a component level interaction. Now, this again takes precedence over a global interaction. And if you have component A and component B, you don't know exactly how they're going to interface with each other, then that's the tool for you. Just choose component interaction, choose, hey, respect all entities on component A to component B and vice versa. And however they end up coming together, respect those. Now, why don't we always just do that? Well, because in SolidWorks simulation, the software has to organize and set up a contact event or an interaction event. So it needs to figure out scenarios for all possible combinations of faces and edges and points. That's going to give you a huge calculation that you're going to have to run. And that's why you'll see that if you have a lot of component interactions, it takes a long time to set that up and run through that phase of solving the study. You may have seen that if you run simulation. So what you're going to want to do is do a local interaction whenever possible and go in to every single contact area or geometry, apply the contact interactions, whether that's bonded, free, or contact interaction, and do that for all the different geometries. And so that's the interaction hierarchy. You want to you take the most priority over the more specific feature or definition, and then you get less and less priority the more general it becomes. So that is the pecking order of things. And it's good to remember that. It goes from specific to less specific. This way, in case you have two competing interactions, the more specific one will take priority. Just remember that, and you'll be okay. All right. So that is the last slide I wanted to show for that. And for the example, I just want to show you where you apply the different interactions to close off my seminar for today. So I want to switch on over to SolidWorks simulation. And I want to show you that location here. I want to open up a quick model. Let's go to this pliers example. Pretty generic. The idea with this is we want to apply a force load on the top and bottom ends of the pliers. And I want to see what happens with my interactions with the pin and the plier arms in the geometry. So what I'm going to do here is, this is the interaction. This is the same workflow I just introduced earlier. We have set up our different materials. We're fixing the faces here of the head of the plier. And then we're applying a force here just on the top and the bottom to kind of pin or push down on both ends of the pliers. That's all we're doing. And for us, this is the important part, this global interaction. So it comes in as a bonded interaction, but because it's a feature like anything else, I can edit that feature. And all I did was I switched from bonded to contact. Now, all these initially touching faces are going to be respecting each other. Now, I can tell that. I can use a tool called interference detection. I think we've all used that tool. There's an option that says treat coincidence as interference, meaning it's going to be able to detect any coinciding faces or touching faces. So I can visually see which faces I'm going to be respecting with that global contact interaction. That's it. Just an interrogation only tool. And then when I run this, I can now go in and I can show and animate that. I can see I'm responding to that area. I can see here my stress is developing. Let's slow that down. I'm getting reaction forces throughout the pin and the two plier arms. Lastly, I wanted to show how you can locally apply interactions. So I want to force the ends of the plier to touch. And for that, I'm really going to bring the magnitude up high, right? I'm going to do 6,000 newtons per face to bring this down. So when I do this, right, we can start to see some development there, some response there. When I do that, before I do that, I need to make sure I apply a local interaction to those small faces that are going to be touching. And this is what you're going to be doing primarily with your larger assemblies in your own simulations. So under connections, I have local interactions. I can right click over any of these folders and say local interaction. And then you make sure you switch this to contact, and you just apply one face to each of those pink and blue boxes on the left-hand side. You click OK, and you're left with this interaction that we have here under local interactions. That's it. So I mean, that's it. This is where it begins, right? For us, this is the bottleneck. So just be aware. This is going to take the most time setting up your studies. If your boss comes over at 8:30 in the morning and says, "Hey Nigel, I need you to set this thing up by 12. Can you give me results by lunchtime?" What you're going to do is look at all the different face pairs and see how much time it takes you to set one up, and then kind of do some rudimentary math and say, kind of project and be like, you know what? No, this is 400 different interactions. I don't know if I can hit that and troubleshoot. So maybe after 4 or something, you can kind of start to get an idea of how big of a setup this is going to take to run. To set it up and then run the study. But yeah, that's like Forrest Gump said. All I have to say about that.